Well, good morning, everyone. We are on, I think, 8, 9, 10, 11. We're on our last, four sections? 4 sections to go. Okay, so we're on our last 4 sections. Yeah, that sounds about right. We finished with the series in the sense of how to test if they converge or diverge. And the last 4 sections are to do with what are called power series. And in particular, two special versions of them called Maclaurin's and Taylor's series. This is a, if you like, an application. And really, to be honest, the only reason we did the first, whatever it is, 7 sections, is so that we could analyse power series. So what are they? Well, they're a very simple definition of what they are. It's an infinite polynomial. So you can imagine 5 plus 2x plus 4x squared plus 16x cubed for eternity. So x is a variable, that's new. And typically when we do series, they're made up of a whole load of numbers added together. But you can extend that idea to what are called power series. Here is a generic way of writing a power series. It would actually be using this notation. If you decide to call them A0, A1, A2, and A3, then you'd use this notation. And any other letter of the alphabet you want, I guess, then you'd adapt the notation accordingly. So one of the things you'll notice is that it's in sigma and that it's a series. Another thing is that not always, but very often, this series will begin at n equals 0 rather than our typical n equals 1. That's really quite cosmetic. But if you plug n equals 0 into here, you see that that would get you a0 x to the 0, which would be a0 times 1, which would get you a0. And if you plug n equals 0 into here, you would get that term. If you plug n equals 1, you'd get this term. If you plug n equals 2, obviously this one, then this one. So this is equivalent to that. Now, right now we are going to look at for what values of x does any given power series converge? So that's essentially our question. For what values of x? Will a power series, such as this one, converge? Now, to answer that question, we are going to be using some tests. In particular, we're going to be using the ratio test, less common, but occasionally after that, the nth root test. These tests will tell us the major values of x. Where this guy converges. But then, we will then use any of the other 7 tests to look at the endpoints. So I'm putting down in English what we are going to be doing today. We're going to be given a power series, and we are going to be finding what's called the interval of convergence. The interval of convergence essentially are the region of x values where the given power series converges. So we're only interested in where it converges. So let's show you an example of one. And which one shall I do? That's quite a messy one. Negative 1 to the n, x to the power of 2n, all divided by 2n factorial. So we'll begin. By using the ratio test. And typically that would be the first one you would try. If I did the ratio test on this, and I just do it the way you do all ratio tests, wouldn't you replace, well, first things first, wouldn't that negative 1 to the n basically disappear on us? And you just plug n plus 1 into what's left. So it's 2 lots of n plus 1 on the top, and it's 2 lots of n plus 1 factorial on the bottom. And then you turn the guy upside, and so you're going to have a 2n factorial on the top and an x to the 2n on the bottom. Does that look okay? I'm assuming that is okay. No one said anything to the contrary. Well, continuing with that then, it's going to be the limit as n tends to infinity. Oh, by the way, have you noticed I've still kept my absolute values? Please remember to do that, because that's important. And you might say, well, why do I need them? Well, I kind of need them because x could be negative 1 or negative 20. So the answer might end up being negative. So keeping those absolute values is a safety feature. Well, let's do some cancelling on this and see what we get. Or maybe not. Maybe I should spend a little bit of time just tidying up a little bit. There, that's probably a bit safer. So 2 lots of n plus 1 give you x to the power of 2n plus 2. 2n plus 2 factorial, that's 2n, that's 2n. Right, now I can move on to, still on the ratio test, making it look pretty, or at least trying to. Do you see that x to the 2n plus 1? Won't it cancel out most of that x to the 2n? Great. And you'd be left with some x's. So 2n plus 2 on the top, 2 on the bottom, you'd left by x squared. You happy about that, where that x squared came from? Cancel, cancel, x squared left. Now 2n factorial is going to be cancelling out this fella. Right, so this guy is going to cancel out this guy, but it's not going to be clean. So if you imagine 2n factorial on the top and 2n plus 2 factorial on the bottom, you'd get 1 times 2 times 3 all the way up to 2n. 2n plus 2 factorial would get you the same start. Yeah, you'd go 2n, but when you also do 2n plus 1 and then finally 2n plus 2. Agreed? So when I do the cancelling, death, all the way down, can you see that I'm left with, that one would die as well, I'm left with these two pieces. Right, the 2n plus 1 and the one after it, 2n plus 2. So I now have 2n plus 1, 2n plus 2. So far, so good. Now, how do we deal with this limit? X is a variable. But for the purposes of calculating what a limit is like, I want you to think of as just an unknown constant. It's just a number that got squared. It might be 42 squared, it might be 42 trillion squared. But in the big scheme of things, it's still a number. So if you have a number over these two guys, can't you basically just brute force it? Just put in infinity. Wouldn't a number over infinity, or x squared over infinity, won't that still get you 0? So this fella has a limit of 0. Now, if L is equal to 0, which is clearly less than 1, doesn't that mean that the series converges? And it converges for any value of x. It doesn't matter if x is 42 or 42 trillion, won't it still converge? So we have found, almost written it down now, for what values of x this power series converges. And the answer, it converges for any value of x, which means its interval of convergence, because I don't want to have to say or write that down all the time, is going to be every value of x. So this power series will converge if x is 2, -2, 42 trillion, American debt, don't matter, it will converge. So we have found the values of x for which this particular power series converges. You might want to call it all real numbers because it's the same thing. In this question, I do not need this end bit where I go and test the endpoints because there aren't any endpoints, it's infinite. Right, it just starts here, finishes there. We call this situation, where it's everybody in the universe, we have a term called the radius of convergence. It uses a capital letter R, not this guy, a capital letter R, and it's infinity. And what that basically tells us, that if you start at the origin, you can go infinitely far on either side, and those x's will work on that power series. Oh, and in case you're curious, that particular power series is a member of the cosine family. I haven't told you that yet. Do you know that every function that you've ever seen from 141 beyond or behind, every single one of those functions is a power series? Sine x can be written as a power series. You wouldn't have thought a trig function was a power series, but it can be represented that way. Okay. Try another one. Keep that one over here for a little while. I guess I'll call that example 1. Here's example 2. Suppose I have a power series n equals 0 to infinity, x to the n over n squared. Then I'm going to find, essentially, its interval of convergence. That means the values of x where this power series will converge. X to the n plus 1 over n plus 1 squared times n squared over x to the n. So far, so good. Now, some cancelling. Would you agree that this guy cancels with this guy and leaves an x? X to the n plus 1, cancelling x to the n. You are going to get an x on the top. I'm not going to do anything about these two guys except multiply out the bottom one. So that's what we get. These two together with an x. Think of x as just a fixed number like 42 again, and just focus on what the heck's happening to this. I know it's a mess, but that says n squared plus 2n plus 1. Would you agree that this guy divided by that guy as n goes to infinity gets you a limit of 1? Which means you are going to get 1 times that. It means that your answer to this limit is whatever the absolute value of x happens to be. And this is more typical. This is what you very often get when you're trying to find intervals of convergence. You tend to have an x or a 2x or an x squared or something like that in. Now, since this is a ratio test, what has to be true about the limit for it to converge? Well, for it to converge, shouldn't the answer to the limit be less than 1? Right? Now, when you take that guy, isn't that all the values of x from -1 to 1? So our interval of convergence right now is values of x, I'm using interval notation, from -1 to 1. Now, if x happened to be 2, that would diverge. If the x happened to be -20, that would diverge, right? It has to be in this very small window. We call this fella a radius of convergence of 1. Because if you go to the center, in this case the center is at 0, and you go 1 either side, you'll generate that guy. And you might think, well, that's the end of it. No. We will then use any of the other 7 tests to look at endpoints. Because there are 2 places that we haven't checked yet. Because at these 2 places, won't the limit be 1? And when the limit is equal to 1, we don't know if it converges or not. That means we've got to figure it out ourselves. So now we've got 2 jobs to do. We need to see if this guy converges when x equals -1 and when x equals 1. So let's see. There we go. Let's see what each one generates. Okay. Let's test what happens when x equals -1. Well, the power series that I have is this fella, right? Well, when x is -1, doesn't this fella turn into that guy? I'll write it over here. I need to find out, does that converge or not? If it does, I will go over here and make a square bracket around the -1 saying you can use that as one of the places where x will converge. If I find out it diverges, I will leave it as a curved bracket. So our last puzzle, the last piece of the puzzle, is to check the endpoints for convergence. Right, looking at that guy, any test, any of the 7 that's left. So don't bother doing ratio test or nth root test, because all you'll get is inconclusive, right? You won't be able to get in and out of that. Does this guy converge or not? Gut feeling.
Shouldn't it converge?
Agreed. Give me what test would you use? How would you prove it?
P-series comparison test.
Do you see that -1 to the n? Won't that kind of kill that a little bit?
Yeah, alternating series test.
That's the one. So can I just say converges by the alternating series test? And you can imagine just, tidying it up and physically doing it, but it does converge. Now, what about when x equals 1? Let's check that guy out. Well, the power series that you gave me will turn into 1 to the n over n squared. Oh, isn't 1 to the n just 1? Right, let's look at this guy then. Does 1 over n squared, sigma 1 over n squared, does that series converge?
Yes.
And what would be the way that you'd go and prove that to me? Because you're right.
P series.
Yeah. So this would be a P series, P equals 2, converges. Great. So the final answer, right? Like in the quiz show, this is my final answer. I'm not allowed to change it. Is that it's all the numbers from 1 to -1, including the 2 endpoints, because I tested them separately. So this power series will converge as long as x takes values of -1 to 1, including -1 and 1. Are we okay? Are we happy with this process? Okay. Then another one. This is going to be what, example 3. So I've shown you a power series where any value of x would work, right? That was example 1. The one we just finished was a power series where it was limited to -1 to 1, right? And by the way, the answers are always intervals. You don't get one of those everybody except 1 going this way and -1, right? You don't get bigger than 1 and bigger than negative. That doesn't happen. It's always an interval, right? It starts here, finishes here. It either starts at infinity and finishes, you know, -infinity and infinity, or -2 to 2, or whatever the numbers may be. Now, in this third example, keep it nice and simple. We're looking at that power series. Now, according to our process, we use, or I would at least use, the ratio test. So it's going to be the limit as n tends to infinity. A little bit different since it's not a fraction. Won't it be n plus 1 factorial x to the power of n plus 1? That would be the top terms. And the bottom terms would look like that. Time to start cancelling. That guy cancels with that, leaves me with an x on the top. I hope you can do this one without too much work. What would n plus 1 factorial on the top cancelled with an n factorial on the bottom? What would that leave you?
N plus 1 on the top.
Right. Now, at this point here, you just make the same assumption we do all the time. Can't we just pretend x is a constant? 42. This one is easy to do. Can't you do brute force on this and just say infinity times x? Infinity. Oh, that's not good news. This power series will never converge. Except for when x equals 0. Power series, every power series in the universe will at least converge for one value of x equals 0. And you might say, how is that possible? What would this look like? Well, wouldn't it look like nothing factorial times 0, 1 factorial times 0, 42 million factorial times 0? Wouldn't you just get a whole load of zeros that all add up to 0? So it might say a bit nitpicky, but it does exist. And that makes R, the radius of convergence, very small. You start at 0 and go neither, you go 0 either side. And technically, the interval of convergence isn't really an interval. Isn't it just a single number 0? So there are going to be 3 situations that you're likely to get when you are looking for intervals of convergence for a power series. you're going to get example 1, where every value of x in the universe works. They're pretty good because then it means it's negative infinity to infinity. You're going to get examples where it never works except for the trivial question or example. When x is 0, everything works, right? But that's the only one. And when that happens, you get this result. And then you get the bread and butter one, where the interval's minus 10 to 10, minus 2 to 2, 15 to 17, right? It's an interval. And in those cases, you're going to have the most amount of work, because aren't you going to have to test the 2 endpoints, because they may or may not work, and you have to know. So in those 3 examples, the ones I've called example 1, 2, and 3, we have pretty much covered all the situations you're going to meet. The numbers will change, of course, the functions, you know, the various weird powers will change, but not the general finished result. So I am looking right now at some examples from the homework, so it can give me some clues. So here is a question. Do you see that this one starts at 1? Could start at 0. They could start at 42. It doesn't matter. It really doesn't. It's quite cosmetic. Right? They should start at 0, but there's no need for it. It's not going to change a darn thing, right? You could almost ignore it and it would be fine. So let's find out what values of x does this series converge from. Well, again, we don't have to worry about fractions. And it's too late to do it, but when I wrote it, I realized I didn't need to. See these -1 to the n's and -1 to the n plus 1s, don't they basically disappear because of the absolute value? So if I'd thought a little bit more carefully before I started writing, this would have been what I would have written. So don't worry about the -1 to 2n's, -1 to n plus 1s, or any of them. The minute you stick the absolute value, they get used up. And because the absolute value of -1 to the n is 1, and 1 times something doesn't really change the something. Okay, time for cancelling. Would you agree this guy cancels with this guy and leaves an x? And I'm going to skip some corners here. Won't that become 2n plus 2 over 2n? And I don't think I need that room now, because if you do that, won't that just basically get you 1? And so it looks like this fella is just the absolute value of x. Now, according to the ratio test, this will converge when the absolute value of x is less than 1. So right now, our interval of convergence is -1 to 1. This interval -1 to 1 is very common. You get a lot of power series. That's the guy. I think the reason that there's so many of these is, in some sort of a ways, as long as the R values between -1 and 1, like a geometric series, doesn't it converge? And I think a lot of power series, although they're not geometric series, they behave in many ways as if they were. So that is half the battle. But don't we have to test the 2 endpoints? Right, so back to doing that again. So let's check x equals -1 and see what we have. Well, this is the power series. When you plug in -1, now you're going to have to play with some weird looking algebra when you do endpoints. So I suggest strongly that the first thing you do is make it look pretty before you even try and do a test on it. Won't these two multiply together to give you -1 to the power of 2n? Now, I can tell you that that is that. Anybody want to chuck in why that's true?
Because the fact that the n coefficient in the power is even means that that -1's always going to be positive, so it's going to essentially wipe out the alternating series effect.
Yep. Now, don't overthink this one. Does this converge or diverge?
It diverges.
Right. Would you agree you could just brute force it and its limit's infinite? Technically, I've just done the divergence test, haven't I? So it diverges by divergence test, right? Now, what about the other fella? Well, if I check x equals 1, I'm going to get two lots of -1 to the n times 1 to the power of n. Well, that's going to end up being this guy, because won't 1 to the n just be 1? 1 squared, 1 cubed, 1 to the 20th, they're all 1. So you get this fella. Does this guy converge or diverge?
Diverge?
Yeah. Is that -1 throwing you? No, it does diverge. I mean, isn't the answer just going to go +2 -4, +6 -8, plus a billion minus, a billion and 2? It's going to be diverges. And I would say because its terms are infinite. And if that -1 wasn't there, wouldn't it just be infinite? If that -1 is there, isn't it just going to bounce up and down between plus and minus infinity, which is just as bad? So this fella stays put because neither of the endpoints converged. So the interval of convergence was what it was at the start, and I forgot to write down who R is. What is R, the radius of convergence for this guy?
One.
Yeah, nothing special, just 1. Do you feel comfortable about this process? Okay, so all I'm doing is finding uglier and uglier guys to do it to. Yeah, this one will do. What am I up to? I don't know, exemplify properly. This power series is going to be 4 to the n, x to the n. Yeah, I'll do. So the ratio test. I think I'll make sure my next one's a fraction. We need to see some more fractions. So 4 to the n plus 1 and n plus 1 over an x to the n plus 1. And then a 4 to the n and n over an x to the n. Okay, Those two guys cancel, but you're left with a 4 on the top. Those two guys cancel, and you're left with an X on top. When you agree those two guys in the middle, as n becomes infinite, right? Won't those guys become 1, right? So I have a little n plus 1 over n thing, but they become 1. So what you're going to be left with is that. Okay. For this to converge, it needs to be less than 1. So this is the first time where we had to do this little tweak. If I want to find the values of x for which that's true, I really want the absolute value of x on its own. So I am going to divide both sides by positive 4. And now I get that. That tells me that the interval of convergence is values of x between negative and plus a quarter. That makes the radius of convergence a quarter. And then I would test the endpoints. Okay. I want to test these two endpoints. So let's see what we have. This is the guy. We're going to test it at negative a quarter. So it's going to be this guy, negative 1/4 to the n. I would split this that way, because won't that allow me to cancel these guys out? And that will leave me a pretty boring looking, I'd put the negative 1 first, that guy, which by the way diverges, because you make that infinite. Can I just tell you, because I'm not going to spend time on it, that this also diverges. So interval convergence is the same value as it was when it started. Radius of convergence is 1/4. Any questions? Are we good so far? I mean, maybe one of the saving graces of this type of question is that it has a kind of flow to it that you kind of follow, right? You kind of do the same kind of things each time. Well, now that you've got comfortable, let's try and make you uncomfortable. When you have a power series that's written like this, we say that it is centered at 0. But you can also have power series that look like that. And those power series are centered at whatever that number there happens to be. So say this is x minus 3, that's 3. It's still considered a power series. And later on, you'll find that we give them slightly different names. And this one will be called a Maclaurin series, and this one will be called a Taylor series centered at 3, but that's just a name. So this is a power series centered at 0. This is a power series with centered at 3. If you want to know what that guy would look like, it'd be C0 plus C1 x take away 3 plus C2 x take away 3 squared for eternity, right? So what we're now going to do is we're going to look at intervals of convergence and radius of convergence of power series that are not centered at 0 but centered at some other number, right? So how about How about this one? Let's look at that one. Nice, easy one to start with. Right. You recognize that as a power series centered at 2. It's got slightly different look. So we are going to use the same test as before. And this is going to give me, in this case, the limit as n tends to infinity of x minus 2 to the n plus 1 over n plus 1 squared. Then on the top, you have this guy, and then you have this guy. When you cancel these guys out, you'll find that there's an x minus 2 left over. If you take these guys and just distribute them a little bit, you get that. Okay. Consider x minus 2 as just a constant. It's like 40 million take away 2. It's just a number. So this is the bit that really the limit wants to deal with. Would you agree that the limit of this would be 1? So the final answer will be 1 times this guy, which means it's that guy now. It's very similar to what you would have got if that had been x. If that had been x, wouldn't this just be the absolute value of x, right? So the math isn't that different. Now, for this to be a converger, according to the ratio test, doesn't this fella have to be less than 1? Okay? So I'm going to solve an inequality using an absolute value, because I want an interval. I want x from minus 2 to 2 or 7 to 22. I want an interval that starts with an x and then it finishes with an x. So I don't know how long ago you've done this, but do you know that is equivalent to saying this? Right? This absolute inequality is the same as this one. Now, if you add 2 to both sides, your interval of convergence, at least our start value, is that. So have you noticed that we shifted the world essentially 2 units to the right, which isn't a surprise. You see how this guy's at 2, you'd expect everything to be centered at 2. This fella here has a radius of convergence of 1. Can you imagine the middle was 2? Won't it be 1 either side? That's what the radius of convergence tells us. Is that question finished, or do you think I've got something that I still need to do? Is that the final interval on convergence, or should I check some things? Agreed, we have to check. We have to check 1, we have to check 3. So let's see what happens at x equals 1 then. If you take this fella here, and you plug x equals 1 in, well, 1 take away 2 gets you negative 1 to the n. I'm getting deja vu. Wasn't that an earlier question? So it converges by alternating series test. Now, suppose I check at the other extreme at 3. Well, this fella, when you replace x by 3, you get 3 take away 1, 2 is 1, 1 to the power of n is still 1. So you end up with that guy. And that one converges because it's a p series, right? So that tells me that both values work. So far, so good. Now, I don't want to redo this entire question, but can we pretend that I just tweaked it a tiny little bit and I made that n? Right, that's the only thing I did. Can you trust me that this would be the same interval of convergence? It would still look like this. And when I plug 1 in, I will end up with sigma -1 to the n over n. And when I do it the other way, when I plug in 3, I'll end up with sigma I'll just end up with a positive, I should say. I'll end up with sigma 1 over n. Can you see that on this side it will converge because it's an alternating series, but on this side it won't because it's harmonic and it's a p-series that diverges. What that tells me is that if I just did that one little change, one side would be usable, but the other side wouldn't. I just want to make sure that you don't think it's always the same on both sides, right? They're always, you can't use them on both sides, or if you use one, you're guaranteed to use the other. Can you see in this example here, one side would end up being used and the other wouldn't. So you have to check both. Because see, if you make the assumption, oh, the first one works, I'll just stick a square bracket around the second one, I'll be fine. Well, maybe you will be, but you know, there are going to be situations where you won't, right? And you'll get caught out. Are we good? Let's scroll a little bit further. Okay. I won't put the intervals in, it's just annoying. They're getting uglier, right? They're getting more and more bits to them. Is our ratio test? Okay. Well, God, I just remembered to not do that. N plus 1 to the 5, x to the n plus 1, 5 to the n plus 1. Turn them upside down. Okay, we got some cancelling. This guy cancels out with this guy, leaves an x. This guy cancels with this guy. Guess it leaves a 5 in the bottom. These two guys, for the time being at least, I'm just going to leave alone. No, that gap's not necessary. Okay, these are considered as constant, so I'm going to forget about them for a while. What's that fraction going to be? What's its limit going to be when n goes infinite?
One.
Yeah. Technically, it would be a lot of work to prove it's 1, because I guess I should FOIL the whole thing out and do L'Hopital 5 times, or multiply it all out and divide top and bottom by n to the 5. Can we just call it 1? Call it good. Which means that 1 times that means we get this guy. Now, this particular question, isn't this one centered at 0? Right. Now, if this is going to converge, doesn't that need to be true? Which in turn, if you multiply both sides by 5, means that's going to be true. So my interval of convergence is values of x between -5 and 5. My radius of convergence is 5. And then I test these two endpoints. And I can tell you right now that they both diverge. But you can check that in your own time. So that's our final answer. Okay, we got this guy done. I'll skip some corners, but we got him done. Now I'm going to do some surgery to him and see if we can make intelligent predictions based on that guy. Right, see if I took that guy, and the only thing I'm going to do is add one more term. I'm going to stick an n factorial in the bottom. Do you think the interval of convergence is pretty much going to be the same as it was here? Or do you think that n factorial might change the game?
N factorial should change it.
Right. Would you expect it basically to make it so that any value of x will converge? And that's exactly what you would get if you went through the math. Suppose I stuck the n factorial on the top and I went through the whole process. But let's just try and predict what we would reasonably assume. So that one I would bet a couple of $100 anyway that that's the answer, but I should check it because sometimes you get caught out. What do you think about sticking an n factorial on the top might do?
Diverges.
Yeah, except for the trivial x equals 0. And the last one, what do you think that combination, which is basically, I've added that. Any gut feelings? Last chance. The choices are, doesn't change at all, ends up basically those two numbers, anything between -5 and 5. It pretty much kills it, and the only value that works is the trivial x equals 0. Or it fixes it in such a way that any value of x will now work. That's your choices.
Any value of x?
And I agree. That's my judgment. Won't n to the n have a much bigger influence than n factorial? Remember the hierarchy of I get to infinity quicker than you do kind of thing? What that can do is that if you have a power series, maybe you start off with this guy, you can sometimes make quite reasonable predictions about what the effect of other power series which are in the same family. To me, the same family is basically the same thing, but with something added, right? Something extra added, right? And you can make reasonable predictions on what is likely to happen in such a circumstance. Okay, let's do one that is centered at another number. Okay, I've lost track of which example, so I'm not going to write the number now. Let's do a sigma of n over 3 to the power of n with an x plus 2 to the power of n. Yeah. So this guy is a power series centered at x equals -2, right? Going to do the ratio test on it to find the values of x where that converges. So in this case, it's going to be the limit as n tends to infinity of n plus 1 x plus 2 to the n plus 1 over 3 to the n plus 1, and turn it upside down. Okay, I'm just going to leave the n plus 1 over n terms. I get a lot of mileage out of the other two. Won't this guy cancel with that and leave a 3 in the bottom? Not surprisingly, that cancels with that, but you're still going to be left with an x plus 2 on the top. Forget about that guy for a minute. This is the guy that we're going to make n go infinite on. Hopefully you do so many of these that it just becomes second nature for something like that. Would you agree that the limit is a third? Right? L'Hopital or whatever method that you use, but it's a third. So we are going to get 1/3 x plus 2, right? That's what we're getting. Now, if that is only going to converge according to the ratio test, if you make that less than 1. Agreed? Now, to make that prettier, we need to isolate the x's. So I'm going to multiply both sides by +3, and that's okay. Can you see now that we've got the kind of structure that we need? So what's the interval going to look like? Well, that's what the absolute value less than 3 looks like. If you take away 2 from both sides, you're now looking at an interval of convergence between -5 and 1. What's the radius of convergence in this question? It's a number. What is it?
Three.
Yeah. How did you do that? What was your thinking process?
It's centered around -2, so the numbers are 3 away from -2.
That's a much better way of saying it than I was about to. I like your way much better. Yeah. It's 3. Shouldn't we be testing the 2 endpoints? Maybe one will work. Maybe both will work. I don't know. Maybe none will work. I'm going to do it, not really do it, but I'm going to kind of do it by looking at what would happen in my head. If you plug -5 in here, won't that become -3 to the, can you imagine the 3 to the n's cancelling, and I'd be left with a -1 to the n, and that's diverging. And if you go the other one, can you trust me, it diverges. So that's you finished. I think you have a saying, it's probably a British saying, but it might be an American one. I've got a feeling that I'm flogging a dead horse here. Would you agree that there's nothing much new happening in the next question, right? I guess there's maybe a little tweaky algebra, but nothing really. Haven't you probably seen every power series that you're ever likely to want to see, and you now know how to find its interval of convergence and radius of convergence? That's what I'm hoping. Okay, so what I'm going to do for the next few minutes is let's look at the homework and just see what those questions look like. Okay, Olivia's got some issues. And if you look at the homework and you say, I'd like you to do that one because I'm not sure I know what's happening, then that would be a good candidate for me to do again, right? Another question. And if you go through them and you think, nah, you've covered the question like that, I think I'm pretty sure I know what to do. So I'm going to, if I can do this from the top. Oh, by the way, when you look at these questions, you should be getting deja vu because every single question asks the same thing. Find R and find interval. That's all, right? Find the radius of conversion R and find the interval of convergence. Okay, would you be comfortable with question 1? Right. Is there anything in question 2 that looks weird to you? Because I see something that I might not have covered, but it's not a biggie. Can you see the 9th root of n on the bottom? I would probably call that n to the power of a 9. You're going to have a really ugly looking thing. It's going to be n plus 1 to the power of a 9 over n to the power of a 9. Do you know that just ends up being 1? Just like n over n plus 1 gets you 1. You know, n squared over n plus 1 squared. Do you know a polynomial over the same degree polynomial gets you 1, and that includes square roots and 9th roots. I think we've covered versions of 3. Nothing major here. Are you okay with 4? Do you think you'd be fine with it? Now, 4 on the bottom is not 3n brackets round me factorial. It's 3 lots of n factorial. Right? So make sure that when you're doing the cancelling, the 3's cancel out. And basically, you're just going to have an n plus 1 factorial cancelling an n factorial, and you'll be left with an n. If they had wanted it to be 3n with brackets round it factorial, which they could have, right? That would be a slightly different piece of algebra, wouldn't it? 3n plus 3 factorial over a 3n factorial. Won't that generate a different cancelling? Right. So brackets do matter. I'm sure I did something like 5. Are we cool with 6? There's one centered at 11, but it didn't really matter. Those answers are bugging me. Okay. There's one. Oh, this is a little bit different. Do you see in this question they give you a choice for the interval convergence? I think I know what's going to happen here. Do you know that this guy is going to have an interval convergence of 0? In other words, it doesn't work unless you make x equals a fifth. So that's an example of a power series that only really works when the guy that's in the brackets is 0. So when you make that guy there 0, which is what this is saying, then this power series works. And it's pretty obvious what's happening. Isn't that n factorial killing its stone dead? Now, if you stuck it in the bottom, it would work for all values, in which case minus infinity to infinity would have been your answer. Do you feel comfortable about 9? Just looking for nods. You feel comfortable about 9? If you don't, we can do it.
Yeah, can we work that one out?
Okay. So I'll just take a little note of it. It's going to be.
Didn't we just do that one? Like a little bit
Oh
ago?
wait, yeah, we did. I was looking at 10.
Okay,
Sorry.
but that's fine. Let's do 10, right? Because that's the one that was causing you. Okay, I'm just going to write this guy down presently. Doesn't matter what number, because they keep changing them anyway, so. Right, that's a good reason why I like to look at the homework, because it's not always clear in my mind that I've done every variation on a question that you could do, and you might have issues with something. That's weird. Would you agree n root n is not a typical situation to deal with? So I'm going to change it before I even start. Isn't n times the square root of n times n to the power of half? 2 powers added together gets you 3 halves. Ratio test. Oh, while the thought's still in my brain, have you noticed that we've only used the ratio test in every single example so far? I'm going to show you an nth root test because once in a blue moon it can happen, right? Just to show you how that would work, right? So after I finish this one, I'll create a power series where the nth root test would be a better test. But back to this one. It's going to be the limit as n tends to infinity of negative 9 to the power of n plus 1 over n plus 1 to the power of 3 halves times x to the n plus 1. And then you turn them upside down. Yikes. Negative 9 to the n, x to the n, n to the 3 halves. I think I'll write it over here. I need more room. Okay, let's see what we get. If you take this guy and you cancel it with that guy, technically speaking, don't you get a negative 9 left? If you cancel this guy with this guy, don't you get an x left over? And I'm just going to leave these two guys alone. Actually, normally I put them at the front, but that doesn't matter. N to the 3 halves on top divided by n plus 1 to the 3 halves on the bottom. What does that limit get you?
1.
Yeah. As long as the leading powers are the same, you're going to get a number. So 1, which means technically I'm left with that, right? But wait a minute, don't absolute values destroy that? So if I'd noticed that, couldn't have pretended that was 9 to the n right at the start, and so I didn't have any negatives to worry about. But we get there. Well, if it's going to converge, it has to be less than 1. If you divide both sides by 9, do you get the kind of standard form that we need? So that tells me that r, my radius of convergence, is 1/9, and that my interval of convergence is somewhere between negative 1/9 and positive 1/9. And then I would test the 2 endpoints. And you're going to have to trust me on this, but the 2 endpoints, actually both of them converge, but you'll have to check them. I think one of them converges because it's an alternating series, and the other converges because it's 1 over n to the 3 halves, or 9 over n to the 3 halves, which doesn't change anything. And that's a p series where p is bigger than 1. So that will be your final answer to the interval convergence, and that's your radius. That work out cool? Let's return back to the, no, we do not return back yet. I promised you a nth root test power series, right? So I've got to keep my promises. So, right, you see that guy? Now, I can find the limit as n tends to infinity of the nth root of that guy. Technically, the absolute value of that guy, which is the limit as n tends to infinity of 2x over n. You see how clean that was? Nth root of 2 is 2. Nth root of x to the n is x. Nth root of n to the n is n. What's going to happen when n goes infinite to this fraction? Big fat 0. Which is good news, because doesn't that mean the interval of convergence is everybody and we don't have to test much? Interval of convergence is everyone and the radius is infinite. So yeah, I can imagine some situations where maybe that would be less work. Could I do that one using the ratio test? Yes, I could. But then we'd have to end up with that magic thing with an E in it and an N left over and some other weird stuff. We go with that very quick nth root test question.
So just insofar as strategy is concerned, it sounds like the only time we'd really look at an nth root test is if you have something to the power of n in both the numerator and the denominator of
Basically
a rational
everywhere.
function, right?
Yeah. So you want n's everywhere, powers of n. You can have n squared there and you can have 2n there. That also is fine, right? But things that look like that. And this is always going to be an x to the n anyway, really. Right? So that's always going to be there. So it's what's happening here, yeah. So if the terms are all powers of n or some type or other, the nth root test will work fine. And probably be easier to do as well, which is the only reason I picked that one. Technically, I could have done that using, well, not that one, but the one before that, I changed it. I could have done that with the ratio test. It would be much uglier and messier, but it would eventually have gotten me the right answer. But I'm a great believer in efficiency, right? So take the easy route if you can see it. Could I do it for this one? Yes. Nth root, nth root, nth root. But doesn't n to the power of 1 over n just get you 1? So that would have worked fine. Okay. Let's see what's left in the homework. Okay, are we comfortable with 11? Can't see 11? Or you're not comfortable with it?
Oh, we can't see it.
You're not sharing it.
Oh, and your mum always told you to share, right? Okay, so am I sharing it now?
Yeah.
Yes.
Okay, so when I say to you, are you okay with 11, that question now makes sense. Are we okay with 11? Does it look anything? It's centered at 3. Would you agree? Apart from that, it's pretty straightforward. Yeah, okay. What about 12? We're almost finished these. What about 12? You comfortable with that one? Okay. I'm going to do a version of 13. Or I can do 15 because they're basically the same. The reason I want to do 13 or 15 is that it's the only two questions where it was a multiple of x's, takeaway number, like 3x plus 1, 2x minus 5, right? That kind of looked at it, and I don't think we've looked at that situation. But before I talk about that, what about 14? Is 14 okay? Would you be fine with that one? Okay, so the one I'm going to do is a version of 13 and 15. I'll just make up my own. These are pretty easy to make up, which means, right, so suppose you were going to do 3x plus 1, right, to the n. Oh, what shall I do? 3n plus 1 to the n. Put an n squared in. That's pretty much what 15 looks like. Put a 2 to the n in, right? There. Yeah, that looks good. Okay, so we are going to look at find the radius and interval convergence of this fella. Now, this guy is not centered at -1. He is centered at a number, but not at x equals -1. What value of x is this particular function centered at?
-1/3.
Yeah. And that's going to become important later on. So, ratio test. Hopefully I've left enough room this time. You're going to have this fella to the power of n add 1, this fella to 1, this fella. And then you turn the other guy upside down. Pretty much same old, right? First guy, second guy. You know where I'm going next, right? I'm going to do whatever cancelling seems relevant. Okay. If you take 3ax plus 1 to the n and you cancel it with 3x plus 1 to the n plus 1, you get 3x plus 1, right? If you cancel the 2 to the n and the 2 to the n plus 1, you get 2 on the bottom. And that's going to leave me right now with those two guys. Right, forget about him. Would you agree that those two become 1 when n becomes infinite? You know, an n squared over an n plus 1 squared. Which means that this answer, right now at least, that's what the limit is. Now for it to converge, that has to be true. This one's got a little bit more work. Multiply both sides by 2. As long as it's positive, you could get away with it. That becomes that guy. Subtract 1 from both sides. You get that. Divide both sides by 3. So the interval of convergence is that. What is the radius of convergence?
2/3.
2/3.
Yeah, this guy becomes important. Can you imagine a little number line where you put negative a third here and you put a third on this side and you put negative 1 on this side? Isn't that distance what we call the radius of convergence? And you got it so quick, you were well ahead of me, right? It was 2/3. Now, to save time, I'm not going to go and do the whole kit and caboodle. I'll just tell you what the answer is. Don't we still need to test the 2 endpoints because they may be squared, they may be usable. If you plug negative 1 in here, it converges as an alternating series. If you plug 1/3 in here, it converges, oh God in hell, it converges 1/2 to the n squared. What would that converge under? 1 or 2 n.
E series?
Well, you could do a comparison to a P series, and you could say it was less than 1/n squared, in which case it would be a comparison, yeah. But comparison to a P series, which ends up meaning that both endpoints work. And so far so good. Are we comfortable that if you were given a question from 11.8 and you were asked, as every single one of them does, to find the radius of convergence R and the interval of convergence, that you'd feel comfortable about the process? Now, there are always going to be situations that you just don't think about, or I haven't thought about myself. But just stick to the process, right? Trust the math. You know, do what you do. You know, do this, simplify it, figure out what happens when n goes infinite, and you'll get to something that looks like this, right? And then work on it to get your interval. Test the endpoints. And R is basically going to be wherever the center is to either of the 2 endpoints. It'll be the same number. There we go. We've shown you power series and we've shown you how to find their interval and radius of convergence. And what we haven't shown you is where they came from. I haven't created one from scratch. So I'm going to create one for you. And there's a very simple rational expression, right? 1 over 1 minus x. And I'm going to prove to you that it has this power series, which if you use n equals 0 to infinity, it's probably the prettiest, nicest power series you're ever going to see. Isn't it really quite pretty? It's just elegant. And I'm going to prove that this guy is equivalent to this guy. Now, I might not say the word equals this guy, but it's kind of to do with limits. Don't you say, you don't say that this thing is equal to 2, don't you say its limit is 2, so it's a little bit nitpicky. So this is equivalent to that. Not saying it's exactly the same, but it, for all intents and purposes, it is, right? It's equivalent to it. So let's call this power series S, or any letter of the alphabet you feel like. Now, if I multiply this guy by x and I get xs, well, don't you multiply all of these by x? So multiply that by x, multiply this by x, multiply this by x. Do you see that you almost get the same guy, but you're kind of shifted one to the right? Now, won't both of those continue just like that for eternity? Now, suppose you take this guy and subtract that guy. Well, wouldn't that be the same as taking the top row and subtracting everything from the second row? Would you agree that you get 1? If you take out S as a common factor, you get that. If you divide both sides, you get that. Which means that that guy, right, is him. Isn't that kind of elegant? We've just discovered our first function, and we've rewritten it as a power series. You can take this guy, right, and you can find its interval and radius of convergence. It wouldn't be too difficult to do, but I've got a time crunch here, so I'm just going to do it in my head. Hopefully I'll remember the answer anyway. Okay. The interval of convergence is -1 to 1, and the radius of convergence is 1. Can you trust me? But you can check that yourself. All power series have intervals and radius of convergence. Some have infinite answers, right? Any value of x would work. This particular combination only works when you pick x between -1 and 1. That's why I'm saying it's equivalent, right? Rather than it's equal to, right? If I try to plug in 2 here, can you see I would end up with a divergent series? That's pretty cool. Now, here are 2 building block guys that we're going to use. This guy is equal to that guy. Let's try and prove it. If 1 over 1 minus x is equal to that, and we have proved that, so we can assume that, I want you to think of x as not x anymore, but think of x as a place value, right? A place you can put stuff. So if I replace this x by negative x, won't that be him? And if I replace that guy with negative x, shouldn't I replace that guy with negative x? And to make it look pretty, you always separate out the x's, and there's your second building block. Well, I mean, it's not great. So far, the universe consists of two fractions that we know the power series for. But I should be able to do some algebra and get some more answers, right? So I would like to know the power series for that fraction. And I am going to use this guy. What would I be replacing this x by to generate this fella? So what would I replace x here to get this guy?
3x.
And so our power series for this guy will be, 3x to the n, great. Which if you separate it out a little bit, is now that guy. So doesn't that, what I'm doing here is very, very slowly building up power series for linear rational functions. So can you imagine I could get 1 minus 2x, 1 plus 5x in the same kind of way as I did this one, right? And I have a power series for it. And every power series will change. This guy doesn't have an interval of convergence of -1 to 1. It might be -1/3 to +1/3. It might be -3 to +3. Looks like our dog she's interested in something. Right. So, sorry about that. Okay. Let's take this guy and stick a 10 on the top. Since I already know the answer to this, shouldn't I just be able to adapt this to get this guy's power series? Wasn't the only change a 10 on the top? So couldn't I call this 3 to the n times 10 times x to the n? Maybe put a bracket around it just to make sure I don't think it's 310 or something. How about this guy? Well, x squared times this guy's, let me try that again. I did part of A and part of B there, right? I want to do an x squared 1 minus 3x. So that's going to be x squared sigma, that guy, right? That's going to be x squared right, x squared, this power series. This is not considered the best format. If you bring this x squared inside, you're allowed to do that. Won't this x squared multiply with this x to the n? If I was writing it down in full, I guess I would maybe write this. But can't we combine these to a single power of x? instead of x to the n times x squared.
X to the 2n.
No, you add. Right? Multiply would only be if it was x squared in brackets raised to the power of n. But when it's two things multiplied, you add the powers. Do you see that you've now got a power series for that guy? By just starting with this basic building block, do you know that I can find the power series for a lot of different rational functions? Not for all of them, but a lot of them. So I'm going to imagine that I would like the power series for that fraction. So the goal here is to figure some way of using one of these two, in fact it's going to be the top one, to generate this guy's power series. And you really should try and do it in little chunks rather than one big go. So I'm going to think of this as being x cubed times 1 minus x squared. So I'm focusing on just getting the power series for this guy first. If you want the power series of 1 over 1 minus x squared using this guy as your building block, it's really basically a substitution. What would I replace this x to get this guy?
X squared.
Okay, so what we're looking at is sigma n equals 0 to infinity, not x now, but x squared. And then I'm just going to do some algebra. X squared raised to the power of n, that does get you 2n. Right, x squared raised to the power of n, that is a multiplication. Right. Now, let's bring this x cubed in. You're allowed to do that. You can pull out common factors, you can stick them back in. And the only rule about sigma is that you can only do it as long as there's no x's involved. You can't pull an n cubed out of it, right? That's not allowed. Now, we can join those two guys together. This guy times that guy, you do not get 6n, right? It's a multiplication. So what you get is this guy add 3. And there is your power series for that guy. Now, when we come in tomorrow, we're going to, look at some more situations like that. But just to finish with, I want to show you something really weird and really cool. I haven't used this guy much, so I'm going to use him right now. Right, if I write them down in full, right, you plug in 0, that gets you nothing, that gets you, so you get 1. Then it takes away x plus an x squared, take away an x cubed plus an x to the 4, right, to infinity. We're comfortable with that, right? Technically, I should be doing squiggly lines here, but let's just forget about that. We'll just call it equals, right? So far, so good. Now, the weird one. What is the integral of 1 over 1 plus x? You should know that. What is the integral of 1 over 1 plus x? Kevin?
Isn't it tangent?
If it was squared, it would be. Last chance. 1 over x gets you log x. 1 over 1 plus x just gets you natural log. See, you were looking for some hard, weren't you? You were thinking some weird stuff.
Yep.
Right, that could happen. Well, if you integrate this, then shouldn't you be able to integrate that? And the answer is yes, you're allowed to do that. Well, if I integrate this, I get x. I get negative a half x squared. I get plus 1/3 x cubed. I get negative 1/4 x to the 4. Oh, don't I now have a power series for the natural log of 1 plus x? It would be nice, wouldn't it, if I could write it down in sigma notation. So I'm going to go back up here, and I am going to use the power rule on this. Isn't the power rule add 1 to the power, divide by the new power? So won't that get me x to the n plus 1 over n plus 1? Oh, plus a c. So the natural log of 1 plus x is this power series plus a c. Great. Wouldn't it be nice if I could figure out what number this c is? Well, if this is true for every value of x in the universe that's usable, then isn't it true when x is 0? Now, what's 0 going to get me? Isn't it going to basically destroy all of these terms? Because 0 to this, 0 to that. So the natural log of 1 plus 0 is what c is. Oh, but isn't that the natural log of 1? And the natural log of 1 is 0, which means if I now go backwards, there is the power series for the natural log of 1 plus x. Now, if I integrated that, which I'm not going to do, but if I did, couldn't I integrate this and get the power series? So if you know the power series of one function, don't you also know the power series of every integral of that function? Right, you integrate it once, integrate the power series once. You want to do the integral of that function, whatever that ends up being, just integrate your new power series. Are you allowed to go the other way? Darn tootin' you. Couldn't you, if I gave you a power series, couldn't you keep differentiating it and get power series of various other things? There are some functions that exist only as power series. In other words, the function is described by telling you what the power series of it is. And that's actually all you need to know. Because if you tell me what the power series of a function is, I can do everything that you would do with a normal function. For instance, have you ever wondered how your calculator knows how to sketch e to the x, or sine x, or cosine x? I mean, it can't store all the values of sine x in a big table, right? Because you could ask for the sine of 1.23456, right? I guarantee that what they have stored in its memory is the power series of e to the x. And when power series works, we've discovered that although it's an infinite series, most of the answer is contained in the beginning. So when you have a power series, do you know you don't need to do it infinitely big? Do you know you can just do the first 10 terms and you'll get an answer good to 8 decimal places? And isn't that all the TI-84 needs? It just stores maybe S8, right? The first 8 terms of a power series for sine. Another unique fact is every function in the world has a power series, and it's unique. So it's not like, oh, you could get a power series for this guy, which is this, but there's another power series that also is this guy. No, this is the only power series of that guy. Right, so it's a 1-for-1 match. In fact, a lot of people spend an awful lot of time analysing power series in math, right, higher level math, to get some insight into what the solution to certain equations and functions are. Because some differential equations, for instance, are impossible to do analytically. They're impossible to solve exactly, but you can solve them using a power series. In fact, off the top of my head, do you know that that integral is impossible to get the exact answer analytically? There isn't a U sub in the world that will save you. We can find the power series of that and then integrate it. And although I won't be able to tell you what the answer is analytically, won't I be able to tell you the power series of its answer? And if that function is interesting enough, then you'll give it a name and you'll describe it by its power series. If you want to look up some quite interesting power series, look up Bessel functions. Kind of interesting, if you're interested in this thing. Right, I think we've came to a really cool stopping point. So when you come in tomorrow, we're going to do some heavy duty find power series of weird fractions, essentially, right? You'll also be asked to find the interval of convergence and radius of convergence. Right, that's what the questions typically do. I am not going to do that bit because I figured out we've done enough of that today to know how to do it. I mean, couldn't you find the power series of this very easily? It wouldn't be a big deal. And in fact, even this thing here, couldn't you do its power series without its interval of convergence pretty quickly? Right. So when we see you tomorrow, that's what we'll do. And before I forget, two things.